This is an overview of the emnlp conference, which I attended thanks to the generous support of Babel. Thank you. In September in Lisbon, which is here, and it's very, very beautiful. This is not actually where the conference took place, but this is where the welcome reception was, and you get the point. It was very, very, very nice. So emnlp stands for Empirical Methods in Natural Language Processing. And natural language processing basically just means getting machines to understand human language. And so this conference was really big and it was really academic. So I'm really going to give a super, super high level overview with just like one or two selected highlights to try to give you a sense of the overall perspective of the field, right? So there's way more to say than anything here. And also because of that, I'm just blatantly using lots of the slides from the academics there. So pretty much anytime you see a slide, just assume that it was produced by somebody who spoke at the conference and embedded into this. Yeah, but so it will be kind of fast and hopefully not too dense, but kind of dense. So maybe just hang on to your seats. But so I figured it might be worthwhile framing it in questions that kind of might get you a little bit more interested in coming here than just for the pizza. So the questions here will be addressed. How can natural language processing be more transparent for practical use? And so this will be the focus of a bit about a tutorial I went to called Transparent Machine Learning. How then this very big question about how can machines learn the meanings of words? And this will be about semantics, and then really like quite a small stub to look briefly at how can we use NLP to learn how humans process language, which will be computational cognitive science. But so we'll start out with just like a pretty high level overview of NLP. So there's natural language processing, but it's this gigantic field. This is only one of like many conferences that happen in it every year. And how can you think of like organizing this research? So there are multiple dimensions that I think are relevant, but I tend to mentally categorize them along these two. So there's the linguistic levels, which should be fairly straightforward to you all, right? It's going from like the various small units, like how do we process the sounds associated with a word, to up into arranging them into higher level structures till you get to a document. And typically, depending on which level you're interested in targeting, you have to use different natural language processing methods. And then these methods themselves sort of exist on this orthogonal dimension between rule-based approaches, which are fairly easy for humans to understand and involve like application of domain expertise, and machine learning approaches. So we'll start by taking a high-level look at what the topics that were covered at the conference in terms of the linguistic levels. So this hopefully is not too hard for you to see. So these are the sessions, the topics of sessions that were there. So like each session had a name like, language and vision or semantics. And there were typically 3 or 4 sessions going on at any given time. And there were like 3 or 4 sessions a day as well. And so there was just like, you get the sense like overall there was a ton of research presented at this conference. And so orange here is papers, which were talks, and green is posters, which is like pretty typical for an academic conference. And here, so you can see why I put at the top, semantics is king. There were at least 50 different pieces of research presented under the rubric of semantics. And so this is like, even though there's lots of other more traditional kind of NLP areas that get processed so I also have ordered these somewhat into the different levels. So down at the bottom, you see like, this is, for example, what was covered in terms of speech recognition, which is a pretty big topic, but as you can see, like really pales in comparison to semantics. So this already should hopefully give you kind of a bit of a sense of where the field is at, like what people are interested in researching right now. There's tons of other stuff here, so everyone who's interested should, maybe put this graph in front of you and peer at it a little bit deeper. and ask me questions about it later. But so this is overall, we're looking at a field where semantics, so this question of teaching machines meaning, is really, really important. And then there's the next two big topics are kind of more generic and multi-level. So statistical models and machine learning methods are huge. Machine translation is a giant task, right? And one that applies at all sorts of different levels. So that's also a big research area of focus. And then computational psycholinguistics is my personal favorite, doesn't get a lot of love here. And fun and quirky topics, I did not go to any of those talks, so I could not tell you what they're about, but I'm sure they were fun and quirky. And so just for some fun also for looking at getting an overall picture, I took the titles of the talks and performed some really low-level NLP on them. So first filtering out stop words, which are words like of and the that don't give you so much information, and then stemming, which is basically a process of removing word endings to try to get the roots. So if you have like the words model, models, and modeling, stemming will remove all of those so you get just model, which is what you see is by far the most frequent term in all the paper titles. So modeling is the big thing. Also not super surprising. Second most popular is use. Don't know what to say about that. Word is not a big surprising one for the third. And neural is pretty telling as well. Translat is the fifth. So this is also just to give like a very high level view of what's going on. So to get to the other part of it, the other dimension, right? So this is kind of an overview of where the attention is in terms of levels. The other dimension, I think, is this rule-based versus machine learning approach in terms of methods. And this is a pretty interesting domain. So before getting into the tutorial that addressed this in particular, I kind of want to give you a sense of what I'm talking about with this. So maybe this example is not so great for people who don't work with regular expressions a lot, but imagine, or IP addresses, but imagine if you wanted to create a regular expression for an IP address. If you're a person who knows what that looks like, right, then you take a kind of rule approach, which is you take your expertise and you translate this into something that matches IP addresses, right? Like, so you say, I know what they look like, so I'm going to craft a pattern that matches these. The machine learning approach would be to infer this from examples. So this is an example of a research project from the University of Trieste that, I think I have this open with data. Yes, so where you can put in data and tell it what you want to match, right? And then run this, and it will give you a classification process that attempts to use a genetic sequencing algorithm to learn the regular expression that matches the patterns you give it. And this is what you get as a result. So this would be taking a machine learning approach. Let me go back to this. So this is an example of like the two different ways that you could approach a problem from the rule-based approach and the machine learning approach. Here you can see a clear caveat is that if you put in different example data, you might end up with a different outcome for reasons that are not entirely clear to you. So this is, but the awesome part is that you don't need to write a regular expression. So this is the trade-off. So we'll explore that more in summarizing this transparent machine learning tutorial. So this was presented in the first days of the conference by a research team at IBM. So I'm using a lot of their slides. They are very enterprisey, but they're but they're pretty good. So the people who built it are behind this system called System T, which powers a lot of different applications and products coming from IBM. So for example, if you know the question answering application Watson, which won Jeopardy a few years ago, this System T was behind that, and so it involves information extraction and for all sorts of NLP processes. So they put up this what's regarded as the dichotomy here. So the rule-based approach is like very human intensive, where you write out how rules work. There's no learning algorithm per se. The domain knowledge is manual. And then the goal for machine learning, which is where they say the research focuses, is to just get humans out of the picture completely. So the more complex the model is, the better. The less involvement humans have to do with it, the better. And the less domain-specific work that goes in is better. And so they point out that there's this real discrepancy between industry and academia in terms of how much people focus on these two approaches. So looking at the task of entity extraction, which is looking at a document and trying to pick out specific people or institutions or just like basically human relevant entities. They look at, on the one hand, the NLP papers from recent conferences in recent decades, and you can see that 3 out of 4 of them take mostly entirely a machine learning approach. Whereas if you look at the systems used by commercial vendors for entity extraction, really the vast majority of them have a rule-based approach. So there's this really big discrepancy between what's going on in sort of the research field and what's making its way into applications. And when looking at that, they say, why is this? So when you're looking, why do quote unquote real systems, meaning systems used in the business world, use rules? And they point out that the things that are good about rule-based systems tend to be requirements in business environments, so that they can be comprehended. If you're an engineer, you can debug them, you can build on them. Whereas the things that are really nice about machine learning, namely its flexibility and the power to reduce human effort, are typically quite nice to have, but do not supersede these requirements, which are very hard to meet if they're too opaque. So they want to advocate something called transparent machine learning, that a way of approaching machine learning that sort of sits in the middle of the two, that involves like interpretability for humans, but while capturing some of the power of machine learning. So I found this overall approach pretty interesting. So they define criteria that make a transparent machine learning approach a good one and a valuable one. And they also kind of order different analysis techniques from simple to complex, and that could be used for the task they're looking at is information extraction, which is very, very spiritually aligned with NLP. It's sort of a subset. So you can see here these different techniques that you could apply, and this maps really pretty well to this this dimension that I put up before. So that I found to be really interesting. There's also they have an example of one application built on top of System T, which is a visual environment for information extraction. So if you're a user and you put in a bunch of documents and you want the extractor to be able to find, for example, entities like universities, they've built this sort of interface which probably could look a little better but in terms of what you're actually able to do, it affords this sort of great transparency in terms of if you want to know why this is classified, for example, as a degree, you can click on it and be led through the path back to the classifier that assigned that probability. And if you find that there's something wrong that you want to change, you can kind of go back into the data and see which data points are throwing it in the wrong direction. It's a really interesting interface to machine learning. And there's this kind of soporific video demo that you can check out if you're interested. So I found the whole presentation pretty cool. And one thing that I really liked about it, or found super interesting, was that they're arguing for transparency and human interpretability from a business case, right? As a business user, I'm interested in knowing what these models are doing. But it sort of mirrors this debate about understanding it from a scientific case. So there's this long-standing philosophical divide in the field of artificial intelligence that is laid out pretty well by Peter Norvig, who's the director of research at Google, in this essay on his blog that talks about basically the scientific approaches to understanding artificial intelligence. So here I've identified what I think are the connections. So like statistically describe it as a data modeling culture, thinks that nature has, simple as maybe like a straw man here, but an underlying model that's can be understood, and the job of the analyst is to choose a model that can be like that mirrors the real model to the extent that's possible, and then try to analyze the data from there. Versus machine learning kind of parallels more of an algorithmic modeling culture that says that it's really a black box that can't necessarily be described by a simple model. And this ends up producing things that accurately model reality but are maybe not easily interpretable by humans and don't make claims to correspond to the underlying process used by nature. In other words, algorithmic modeling describes what does happen but doesn't answer the question of why. Yes?
But machine learning, if you take linear models, for example, you can like...
Well, linear modeling is not what I'm thinking of when I'm thinking of machine learning. That would actually belong more to the data modeling culture than the algorithmic approach. Like linear regression is not a black box, right? I'm talking about like black box approaches.
Well.
Yeah, there's like the terms get used in these different ways. So machine learning is viewed as like a spectrum, right? That heads more towards the black box, and that's what we're talking about here, is like further down the spectrum. I mean, the whole point of the transparent ML tutorial is like that you can combine them, to like more greater or lesser extents. But as I will show you, the black box approach is like really, really dominant in the field today. So it's a pretty big question. So it's interesting that it mirrors this sort of scientific debate, right? So Norvig is pretty much in this essay ends up coming down on the side of the algorithmic modeling culture, right? The black box, it just has to describe the data. It doesn't have to describe it in ways that we understand. Whereas there's a lot of very prominent figures in the history of AI, including Chomsky for linguistics and Marvin Minsky for symbolic artificial intelligence, that have historically advocated for the other approach, for the importance of symbolic cognition. So I think it's pretty interesting that there's this division in terms of the goals of business use cases and the goals of scientific research. But both of those are sort of losing out at the moment when we look at the field of semantics. All right, and so semantics is pretty important. It's just like the meaning of things. It's why language really exists. We wouldn't be making all these sounds if people weren't having representations about what those sounds mean, right? And so Barbara Pardee is a professor of semantics who says, I would suppose that really knowing semantics is a prerequisite for any use of language to be called intelligent. So then that sort of raises the question, like, what does really knowing semantics mean if you're a computer? Like, what is semantics and what is meaning for a machine? And how would we assess that if we want to see whether a machine is processing meaning in any way that we can understand? So typically for NLP tasks, you try to get things that you can correlate with human judgments. So this is taken from a tutorial about semantic similarity from the beginning by David Jurgens and Roman Pilavar, which was an overview of the current state-of-the-art techniques in evaluating semantic similarity. There's tons of pages in their slides, and I will just steal a few. But the basic idea between this is that maybe you can evaluate how machines are learning by seeing how much their judgments align with humans about what things mean similar things. So if you have the boss fired the worker, the boss fired the employee, and the supervisor let the employee go, a human would typically evaluate these things to be pretty similar. So like all saying, very, very, maybe fine-grained distinctions in meaning, but like the basic proposition could be said to be more or less the same. And then if you have the supervisor reprimanded the worker, like this is kind of similar, but it's not quite the same. There's a little bit of a difference in what's being conveyed. And then the boss promoted the worker is clearly related because you have similar entities, the same entities involved, but the action that's going on is different. So it's not similar. Like it's related but not similar. So the idea is, can we get machines to produce judgments about strings of words and their meaning and how related they are that mirror humans to the greatest extent possible. And so the state-of-the-art technique in doing that today is to use vector space models to make word meaning readable somehow. So strings, these sequences of letters alone are not enough. I think we can say that, like, certainly, like in Babel, there are strings of texts going all over the place, but nobody thinks that our system knows what they mean. So how can you make a string into something that a system will actually understand? So the vector space model basically translates words into a mathematical machine interpretable format. So in this, like, imagine you have a vector space where, like, dimension is food, this dimension is money. Pizza scores pretty high on food, low on money. Bank is the other way around. And then a restaurant, since it has since it has elements of both, is like a little bit in the middle. And so this would be 2 dimensions, but you could extend this, right, like indefinitely as much as you wanted. And so this is basically the main technique, like vector space models to make meanings interpretable to machines. So, but like, where do you actually get this value? How do you know that pizza has more to do with food than money? Or, and vice versa. So the main technique is to get a distributional representation, which means getting words from a surrounding context, which is not a very new idea. So there's a quote from Firth in 1957, "You shall know a word by the company it keeps." And what this means in practice is if you see the word banking, you take the words that surround it on either side and say, this is the context. This is the distributional representation of this word by all the places that it appears. So you take these and then you do some processing to them, and currently what you do to process them is turn them into neural embeddings or word embeddings using neural nets and deep learning techniques. So this is the state-of-the-art approach, and we'll go into like what that is next because it was also the keynote. But just to say, this is how there's a lot of other techniques that are covered and have been tried and have been represented, and this is the one that currently wins, and that was also the one given by the keynote speaker. So the keynote speaker on the first day was Yoshua Bengio. He is a professor at Université de Montréal, and his keynote was deep learning of semantic representations. And so all of the things you see here are taken from his slides, not the ones he presented, unfortunately, because the whole emnlp conference website is down. And like has been for weeks. So these are all scraped together from like other things he's presented in other places, but basically said, well, he was there too. And this picture is from this Wired article, which if you're more interested in knowing more about deep learning and the kind of research behind it, you should read that, which involves him and other researchers. And so deep learning is machine learning algorithms based on multiple levels of representation or abstraction, and this has been used successfully not just in natural language processing, but really everywhere and like everything. It's sort of taking over everything in artificial intelligence. And what does a deep learning architecture actually look like? So one way to paraphrase deep learning might be just horrendously complex, or if you're an engineer, you can think of it as something you really, really do not want to debug. So so you put data in the input layer, and then you have some layer of hidden nodes. So this is like a neural net, and at each layer, it takes inputs from all of the other previous nodes and then uses this. Each node does some little calculation with this and then processes pushes the transformed result onto later nodes. What makes it deep is that there is more than one hidden layer. So if you just had an input and an output layer, or input and then one hidden layer, it would be shallow and you would just be laughed out of this conference. But having multiple means it's deep. And and it's very cool, and like lots of fancy equations are involved. But this is really what happens: is you put in some input data, you train a bunch of these nodes to these parameters, and then you end up with the output. And then at the end of the training, you have this model that's really, really good, ideally, at doing all sorts of things. So I'll just show you some of the things. So one of the breakthroughs of applying this was to language. So if you put in all the data at once without taking sequence in order, then this doesn't work so well for language, right? It's because man bites dog is a different sentence than dog bites man, despite having all the same words. So in order to actually get something intelligent for language, you have to have some way of applying this neural net to in a sequential way. So that has led to the development of recurrent neural nets, which are also so hot right now, in which you have a net for like a node for each time step, and the output proceeds in more or less like a sequential fashion and can be used to model different states in a sentence. Let me see, what is the next one? Okay, so here's an example of how this looks in practice, as well as an additional thing. So the thing that he was actually presenting, like the breakthrough of the recent year, was the addition of an attention mechanism at each step as well, so that which sort of weights different nodes differently at different steps. So basically tells you at each kind of set step in the sequence which other steps should you be paying attention to. For example, if you're at economic, maybe growth is more important, but in is not very important, things like that. And so this is an example of it being applied to machine translation. So your input is economic growth has slowed down in recent years, and then you end up with French, la croissance économique, etc., etc. So this is, it does a pretty good job at machine translation. It actually, without any explicit syntactic structure, it learns things like word ordering reversals. So in this case, you see that it learned the fact that économique goes after the noun in French, even though it appears before in English, which is pretty impressive without anybody actually telling it that. And it also, for German, it learned the syntactic inversion for putting the verb at the end in Nebensätze, which is also pretty cool, given that with no input telling it to do that. You see the really impressive results when you start applying it to images. So here, not the same exact nets, but the same mechanism is being used to generate captions. So you put in, the input is this picture, and the output is the caption, "A woman is throwing a frisbee in a park." So it's really, really impressive. And the coolest part is that since you have this, this is where we are. This is the closest part, I think, to natural language generation that appears in here. So jigyasa, I hope you are satisfied. But the cool thing is that also with this attention mechanism, we can see where it is paying attention in the image at different steps. So at the frisbee step, this is where it's looking. At the dog step, this is where it's looking. Or like where, these are like where it finds the features that are important for in the image for determining like the word that's produced at that step. And then this is the same, I mean, doesn't even have to be in the foreground, right? Like a giraffe standing in the forest with trees in the background, and here are the trees. Yep.
What did you use as training data for this example? Is this the same training data for all the...
I invite you to look at all of Benchio's talks later. Like, it's the same, you mean the same training data for all these images? Yeah, like the same model is producing all of these. There's also a less impressive slide afterwards that where he shows some of the less impressive results, but they're still really good. Yeah.
My question would be, is that really semantics that it knows? Because from what I understood, these machine learning things just learn the syntax, the structure. Basically, this is a translation from the syntax of an image to the syntax of text. It does not understand the meaning, so it couldn't, for instance, tell what will happen next in this picture, right?
Yeah, I mean that's a pretty good question, and it's actually driven home by so another slide that he had in his presentation that I don't have here because I don't have his original slides, but he is like, here's how this problem is approached in classical AI, and he's like, look at all, and it lists all these rules and all these like calculations, and he's like, and here's all these symbols that refer to like linguistic semantic concepts that I don't even know, and like the implication is just like, who cares, right? Like you guys learn how to like decompose semantics into meaning, and I have like built something that just blows it all out of the water. So like I never need to learn linguistics. It was definitely a moment of like throwing the glove, throwing the gauntlet, so to speak, in the keynote. So that was exciting. It prompted a lot of discussion. Yeah, so that's like where things are in the like deep learning center of gravity of NLP right now, which is like exciting, and then but then like how important it is you think to like what semantics is depends very much on how much you accept this as being as qualifying as semantics, right? So I wanted to so it's basically, my summary of it is that the deep learning approach is that semantics for machines does not necessarily have to, or like it can look like semantics for humans in sort of superficial ways, but like the underlying mechanisms might be things that we just don't recognize at all. So I thought it would be interesting to contrast that with another paper that took a more linguistics informed approach of saying like, can machines actually learn like human semantics the way that like humans decompose them? So there was a paper that I found kind of interesting about semantic proto-roles presented by this group from Johns Hopkins. So the presenter was actually Benjamin Van Derm, who's a professor of computer science there, who I would describe as a very convincing humanoid. I really liked his talk. so traditional like theoretical linguistics has these semantic roles, or they actually call them theta roles to be cool, but computational linguistics calls them semantic roles, so stick with that. So you might have like, say like for a given verb like hit, roles are the different like individuals that you can support in relation to that action. So say John hit the tree with a stick. Here John is the agent because he's the one doing the hitting. And if you have something that's someone doing the hitting, you also need something that's being someone or something that's being hit, and that's the tree, and that's called the patient. These are like historical names that I don't know why they're called that, but agent and patient are pretty standard. Like every time you have an action in a subject that's something of the action, it's an agent and a patient. The instrument is what you're doing it with, and then there's this optional role result, which doesn't show up there. But so this is like traditional semantic roles from theoretical linguistics. And so his group started there and dug a bit deeper into theoretical linguistics to find Dowdy, 1991, who has this idea of proto-roles and saying, well, maybe, we've been struggling with like getting semantic roles to work. So like the task is to try to train a model to take a document and say, be able to label the entities for their semantic roles there. So like if you had like a document talking about Goldilocks and the Three Bears, right? Like you'd want the content, the model to be able to tell that like Goldilocks is the agent of going into the house, but the bears are not, they are the patient, et cetera, right? Like you want it to be able to find out these roles. So Dowdy says like maybe they're actually not discrete categories, maybe they're distributions across features. Like so maybe like an agent is someone who's likely to be aware of what they're doing and making things happen and like moving, and then these are like less likely to be the case for patients. Patients are more likely to be holding still and not making things happen. So he says maybe we're, theoretically we can decompose them into conceptual features and think of them that way. So this research team started there. Like they started with theoretical and psycholinguistic evidence, and they gave a bunch of people, they collected a corpus of data by giving people in Mechanical Turk sentences like, an assassin in Colombia killed a federal judge on Medellin Street, and says, for the federal judge, how likely is it that this judge chose to be involved in the killing? And the Mechanical Turk person would presumably say, well, not super likely, so maybe like one of these. How likely is it that the killing caused a change in the judge? And you're like, well, based on my knowledge of killing, like pretty good, so maybe one of these. And so they did this for, they got this for like just gigantic, hundreds of thousands of judgments on different sentences, and they took this and they checked it against the lab evidence and found, first of all, that it replicated, which is like, yes, science, very nice. And then they took these and used them and translated them basically into like a vector space in terms of this is just strings of people's judgments, right? So this is feature space, and they turned it into something that like machines can theoretically use, and then use these in different sentences, to train them as computation, like semantic roles, to say like, what is the likelihood that in this context, this is the agent, the doer of the action, and this one is the unfortunate person having the killing done to them, and so on and so forth. And the nice thing about this is that it produces a computational result that humans can understand, right? So you can look at this and say, I know why the assassin in Colombia is, the actor here. They're clearly like aware of what they're doing, acting with intent and sentient, and like these are all features that we generally associate like semantically with being an agent. So this is kind of like how theoretically human semantics look, and this is kind of on the other end of the spectrum completely from the deep learning stuff. But it's also complex in its own way, right? Like there's all these different levels in the rule-based approach too. So that's the overview for the what's going on with teaching machines human semantics. So the pro is that it's interpretable and we know what's going on. The bad thing is that it just does not perform as well as these black boxes. So I'll quickly move on to the stub for the end. But so the sub part that I was really interested in was computational cognitive science, and where this question is like really important, because so if you're using NLP to try to understand things about how humans process language, you kind of really want to know what's going on, right? But this hasn't actually stopped people from applying deep learning techniques, as we'll see. So yeah, so like the question is, so machines are learning, but like how do humans learn human semantics anyway, right? So like, here's like a baby with a bunch of things around them, and they say, and the parent is saying like, look, it's a Zav. Point to the Zav. And by not knowing what a Zav is, you are in the exact same condition of the baby, who also wouldn't know like what point to the block means, or point to the horse, right? Or like the real world of like children is this like giant multi-featured scene, and whenever like somebody is talking to them about some part of that scene, they really have no way of knowing which part they're talking about. So this is this was the topic of the keynote for the cognitive science speaker, so Afra Ali-Shahi. Her stuff was quite good, and talked about cross-situational learning, word learning, so trying to figure out, using like the deep learning modeling, the impressive stuff we saw before, how to figure out the elements of meaning in visual scenes. So it's sort of similar stuff, right? Like boy is playing on the swing. As a child, if you see this picture and your parent points to it and tells you that, you need to figure out which part of this is the boy, which part is the swing, and which part of this is like playing, and which part of it is on, and it's so on and so forth. And so as we could see from earlier, like deep recurrent neural nets have made a lot of progress in doing things like this. So she has taken that approach and tried to broaden them to extend it to associated concepts such as a human would use, because you'd see this and you'd not see just like a boy, like you might associate this also with like a boy as a child, and this is a play on a playground maybe, and so like this broader context, which is a signature of like human application of language. And so she has worked on modeling this to do the similar sort of thing. So like, what are the concepts associated with this scene? Bicycles, riding, trailing, cheering. So cheering is an interesting thing because there's no cheering involved with this scene, but if you think of like real world scenarios, like it's not implausible, right? Like that would be there. So this is the kind of extension that is going on of like, what can these tell us about, how to branch out into human cognition. And this is just a little sneak teaser to say that there will be probably more about this, because I have this friend who researches more like very similar topics, computational cognitive science at MIT, and he's in Berlin for a little bit, and I'm attempting to get him to come speak here. So hopefully you'll hear from a real expert more about this stuff, and that'll be fun, and hopefully you'll all show up there. But yeah, so that is pretty much the real thing. I'd say the takeaway from the conference as a whole is that the data modeling culture associated with symbolic linguistic structures and like knowing what's going on and like being able to interpret different parts of the processing and the machine learning algorithmic modeling culture are right now in a fruitful, if somewhat uneasy, coexistence. And there's still a lot of interesting stuff happening on both sides. And hopefully we'll, get to take part in some of that one of these days. So thank you for listening. Are there any questions? Okay, we'll forget about that now.
Are there any implications for language learning? Do you think there's, I don't know, apps that generate language learning content by themselves?
Well, are there? I think there's a lot of like implications for everything. I mean, the thing is that there's like, as sort of like, as sort of hopefully conveyed by this slide, right? There's lots of different like levels at which these techniques can be applied, right? And for different tasks. And so far, like, task-specific and like domain-specific things, right, are working well. Yeah, I mean, it depends on what like the task is, and this is something that also is kind of characteristic of the field as a whole, is that evaluation is quite hard and quite a moving target, and a lot of these techniques, when you evaluate them on a different level or on a different task, will suddenly tank in performance. So this was a big topic as well, was collecting data for evaluation and how to actually like credibly say that you've come up with some result. So that was a big thing. So I think like the kind of diverse nature of the tasks involved, and the fact that we don't have a lot of super generalizable solutions yet, although deep learning is definitely like making its bid for being that solution, suggests that, yeah, I mean, like for language learning, it's a matter of figuring out what is the best thing to apply where, right? And because there's just so many dimensions.
Duolingo is machine evaluation.
You can see it.
Right. So yeah. So like for example, right? Like generating language for a for like a language learning task is like not, I would say like that's not the first use I would go for example, right? Like I think there's lots of other ways to use this kind of intelligently without going that route. I have a couple of linguistics degrees, so I'm very sympathetic to people who think that knowing things about linguistic structures is valuable. Like when Benjio had that slide, I was sort of like, and it was like, no, and then just went off and denounced it to everybody I ran into after that. So I'm very like appreciative of the power of what's going on with the deep learning approaches, but I'm also very like have personal experience with the power of like knowing what's going on. So more towards that end. Yep.
That's different approaches on what you want to do. So some people are just interested in, making algorithms who can do scene recognition, whatever, and they don't care what the algorithm does. They just want a solution. And I mean, you can combine deep neural networks and try to understand what the layers are doing.
No, certainly, of course, right? Like that's totally fine. The only annoying thing is when the people who don't care about what it's actually doing come into a conference of people who do care and be like, well, none of that matters, right? Like that's it's great that deep like that like neural nets are so wonderful applied to different levels, and I think there's a lot to be learned there for sure. But it's just that like it does not replace like the theoretical work that's already been done, and that's the sort of tension that's there.
Cognitive scientists who train neural networks, deep neural networks, and they know what each layers mean, and they have interpretations for that. So.
Depending, right?
I mean, there's for example, scientists who did which is called slow feature learning, and he made a deep neural network, and he just put random images into it, and then he saw that some of the hidden layers resemble different, look very much alike different layers.
Right.
Cortex.
No, exactly, and you can see the ones that like the layers that respond to like lower level features like alignment, right, versus like higher level structures like faces, like when you get to face detection algorithms and stuff. Like certainly there are things that are there, but in the specific case of language, like they are not interpretable.
Okay, yeah.
right? Like and this is where the debate really is. Like they are so they're like a general purpose tool, right? And like that is doing really, really well. But the question is like, what do they say about when it comes to language? Right. Yes.
So for the machine learning part in natural language processing, let's say I want to create a machine that does how big is the knowledge about how to construct a deep learning machine? So do they already figured out what is for a specific case the right number of nodes and layers, and I don't know, the range of weights that it needs to be used, or is it all? How much of it is luck and trial and error versus a scientific approach?
I mean, in practice, a lot of luck and trial and error. in practice, I think like you can come up with architectures that are theoretically motivated, but I think it's a little bit more common to do a push and pull where you're like, oh, I think it might be 3 layers because I've come up with this reason, and then I train a bunch of models and I find out, oh, it does best on 5 layers, and it's like, well, I can come up with a story about why 5 layers is plausible, like no problem, right? But this is part of the yeah.
Well, 5 or 10 years ago, I think people said that. So you were already seeing that the results from these things were really good.
Mm-hmm.
The problem was that it was like 5 or 10 people who could do this because
right.
that's
and
smart.
And now most of them work for Google. Yeah. Well, if that is all, thank you for listening. Get some more pizza.